All right, so we're actually going to work through the slow air resistance example from the very end of last lecture, and that was this differential equation. dV by dt is -10 minus v over 5. So let's first get some values for dV by dt. What I'm going to do is calculate some values, and then we're going to sketch a slope field. So when dV by dt is 0, then I'm solving this equation, right? 0 equals -10 minus v over 5. So that's v over 5 is -10, and v is -50. What is important about dV by dt equals 0? That means my velocity is no longer changing. So this is actually a terminal velocity. If you think of something being dropped or thrown and then let to fall in the air, if there were only gravity, it could continue to accelerate forever, and as long as you had more space to fall, it could fall faster and faster and faster. But because of air resistance, at some point it can't fall any faster. So here's our speed limit due to air resistance. This is gravity balances air resistance once we're going this fast. And we can't go any faster. Okay, let's calculate some other values. So dV by dt, I'm just going to make a chart. For v, you could solve these all the same way. Plug in values for dV by dt, solve for v. They're all linear equations. So for 1, no, let's actually go, I'll make the chart like this. -2, -1, 0, 1, 2. So for 0, I've already calculated -50. For -2, I get -40, -45, -55, and -60. Okay, this is good enough. Oh, there we go. So I'm going to sketch my slope field up here. Hold on. Let me make this line up with one of the lines. Okay, that's good. And then I'm going to put my t-axis actually up here, since a lot of these are negative. 0, so I'll make each of these worth 10, -10, +10, 20, 30, 40, 50. There's -60. Okay, and then so at -50, we have slopes of 0. So these are little horizontal arrows or line segments. -55, we have slopes of 1. I'll try to make that 45 degrees. -60 is steeper, slope of 2. And then -45 is a slope of -1. And -40 is a slope of -2. These aren't great, but it's close enough. Okay, there's my slope field, and as I go higher, I get even steeper. So I think previously I've only drawn a slope field where the 0 lined up with the 0. That's a differential equation when you don't have the constant term. If you add in the constant term, then the whole slope field gets shifted up or down. And then I can draw some solution curves. Here's the equilibrium solution curve. So this is interesting. If you get thrown, this would be thrown with a downward speed of pretty fast, -50. So maybe the slow isn't so slow. So maybe we didn't choose great numbers, but that's all right. If you get thrown down with a speed of -50, then you're never going to change speed here. You're already at your terminal velocity. Gravity is balancing air resistance. If you get thrown down with a larger speed than the terminal velocity, then you're going to slow down. You're going to still be falling down, but you're going so fast that the air is slowing you down. So you'll still be falling, but you'll be falling a little bit slower. And, if you were falling with a very large negative speed, you would slow down very, very quickly. You would still be going down. You're never going up. But you slow down very, very quickly, and this isn't great. None of these intersect. They all tend towards -50. So my scale isn't great here, but that's all right. And then if you're thrown down with a slower speed, then you just go faster until you get close to -50, and you can never go faster than 50. Here's a very small negative speed. Then you accelerate till you're close to -50. And then if you're thrown, 0 would be dropped, and then positive would be you're thrown upwards. And you're very quickly not moving upwards due to gravity. And you start moving downwards and accelerating again until you get close to -50. And none of these intersect, they all just tend towards -50. That's just a sketch. Computer could do it better than this. Okay, so v of 0 gives us the initial velocity. That's if you're thrown up, dropped, or ejected down. You might be in a plane and they actually throw you downwards. That's all of these negative initial velocities. You get thrown down. And some of them you slow down, some of them you speed up. Okay, and then let's actually do something that requires a calculation. So we might ask this: if v of 0 equals 10, when does the object reach its maximum height? I'm sure you've seen these problems in Calc 1 whenever you took that. Maybe it was a while ago. But we reach our maximum height when the velocity is 0. Right, think about that. If you're in free fall, if you get thrown up, then your velocity decreases until you're at the top. Your velocity is 0, and then your velocity starts to be negative. You start to go downwards. Right, you're falling. I'm drawing this in 2 dimensions, so you have some horizontal component of your motion as well. But you get thrown. You're not moving up or down here, and then very suddenly you're moving down, and then you move down faster and faster and faster. Okay. So we have dv by dt and v here, so that's no good. If we plug v into there, that we can solve for dv by dt. We can solve for the acceleration at the top. And actually, that is kind of interesting. So dv by dt is -10 plus 0. So if we don't have any speed, then the acceleration is just acceleration due to gravity. Okay, this makes sense. But we can't solve for this when, just from this equation. So you actually have to solve the differential equation and get a differential equation, an explicit function, v of t. So let's do that. I'm going to multiply both sides by 5 just to make this easier. 5 dv by dt. And then we only have one technique for explicitly solving differential equations, and that's separation of variables. Luckily, that works here. We're going to divide both sides by 50 plus v, and then multiply both sides by dt over 5. So dv over 50 plus v is negative dt over 5. And then we can integrate both sides. Continue over here. We're going to get natural log of the absolute value of 50 plus v is negative t over 5 plus some constant. You only need the constant on one side. And notice we divided by 50 plus v, so we have this little domain thing where v cannot be negative 50. Note that is the terminal velocity. So we might want to take care of that in a minute. And then this is the power you put on E to get this thing is this thing. So the power, if I put that power on E, I get absolute value of 50 plus v. And then this is the same as e to the negative t over 5 times e to the c. So I can write that as some constant k. K e to the negative t over 5 equals absolute value of 50 plus v, and note that e to some power is always positive, so currently we have k greater than 0. But now I don't want to write it with this absolute value, so if I just allow k to be negative, I can get rid of the absolute value, and in fact if I allow k to also be 0, I can get rid of this v cannot be negative 50, because negative 50 for v will put 0 on this side. Great, so I can rewrite my solution as k e to the negative t over 5 is 50 plus v, no absolute value, and k is any real number. And if I wanted to write, it's not always necessary unless this is the final thing they're asking for, but I can write an explicit solution, v equals negative 50 plus k e to the negative t over 5. And that is actually, all of these solution curves are a graph of this function for some value of k. If we pick one value of k, we're now on a specific solution curve. Okay, what did we want? We wanted v of 0 to be 10. So I'm going to substitute the point 0, comma 10 for t, comma v into here. And on the left side, I get k times e to the 0. E to the 0 is 1, so I just get k equals 50 plus 10. So k is 60. So now I'm forced to have k equal 60. So 60 e to the negative t over 5 is 50 plus v. That's, I'm on a specific solution curve. In fact, I'm on this one, v of 0 equals 10. This is that curve graphed for k equals 60. Okay, and then what was the question? When does the object reach its maximum height, which we said happens when v equals 0. So now I can sub v equal to 0 into here, and then I get 60 e to the negative t over 5 is 50. So e to the negative t over 5 is 5/6. And then this means that the power I put on e to get 5/6 is negative t over 5. So t is negative 5 times the natural log of 5. Oh, this is off the screen. 5/6. And luckily this number is negative, so that's good. I put that into a calculator and I get approximately 0.91. So what does that mean? That means if I throw my object up with a speed of 10, I think we're in meters per second, but we didn't really specify, then in less than 1 second, I'm at the top of my trajectory and I'm already falling down and accelerating downwards.